Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Welcome, this is Mr. Simon, and we are still talking about senior 4 work. Thank you very much for tuning in. Last time we had talked about the discovery of our subatomic particles, the structure of the atom, and today we are going to be talking about mass number, atomic number, and the isotopes, including isotopic mass. So quickly, let's go, and I want to ask you a simple question about the definition of these three terms, that is atomic number, mass number, and probably isotopes, this time not isotopic mass, not isotopic mass. So who can define for us the term atomic number from our O-level work? From our O-level work. Yeah, we said atomic number is actually the number of protons. What about mass number? Mass number, yeah, mass number is the number of protons and the neutrons in an atom of any element. What about isotope? Isotopes. Who can define for us isotopes? So isotopes. So yeah, isotopes are atoms of the same element having the same atomic number but different mass number. Yeah, thank you very much for that. So we are just going to pass through our definitions here. So we have atomic number. That atomic number means the number of protons in the nucleus of an atom of an element, or the number, and we need to note that the number of protons is equal to the number of electrons for a neutral what? Atom. Then mass number, we say the number of protons and neutrons in the nucleus of one atom of any element. So from there, we try to talk about the difference between how we can get, if you have, for example, mass number, how can we get the number of protons? So we say mass number of actually neutrons. Neutrons, so we say here that the number of neutrons is equal to mass number minus atomic what? Number. And then we have a representation of our element. Yeah, let's look at something on our blackboard. Like, for example, here we have, this is our element, So normally, if this is our element A, well, let's use Z, because A, you can call it, normally we put the mass number up as, these ones are the ones we have. Let's leave them. So let's take an example of X. Let's use X. So we say X, normally we put the mass number up, which is our A, and the atomic number down. Or we can take an example, Ig. For example, let's take an example of sodium. Okay, sodium, and we put 2311. But sometimes they can also write, depending on the periodic table, they can put sodium 11 what? 23. So what for you need to know is that normally the mass number is bigger than the atomic number. And since the mass number is bigger than the atomic number, you can easily recognize that the big one is the mass number. Is the mass what? Number. Then from here, because we have said that we have looked at the definition of atomic number, and we have said atomic number is the number of protons, and the mass number is the number of protons and neutrons. So we can easily get the number of what? Number of neutrons, number of neutrons. So it will equal to the mass number 23 minus the atomic number, which will be 12. So we can look at a simple illustration, or we can make a simple table and revise through quickly about atomic number. Like for example, if they have given us elements, can they give us elements? Or if they give us a table and they tell us, complete the table. Complete the table. Complete the table. And they give you, for example, atomic number. Atomic what? Number. They give you here. Can use our ruler, but it will waste a lot of time. Let's use freehand only. So we have also mass number. Mass number. We have our mass number. Then let's take an example. If we put, for example, P as the protons, so we are going to say P is number of protons because of our space, and the E number of electrons, and the any number of what? Neutrons. So we do like this. This is our table. I'm going to take some elements maybe I know. Like for example, if we take an example of calcium, calcium has atomic number of 20 and the mass number of what? 40. Then we do like this. Make sure you don't look at the periodic table. Then let's take an example. If we have another element, we can make like 4, I think. Let's take 4. Just to revise through. Revise through. Then let's take another element. For example, carbon. Carbon, then we put here, number of protons, let's put 6 here. Put 6. Supposing we put 6 and what? And 6. Yeah. Then let's take another example. We are trying to use the simple ones because they're the ones easier to remember. Let's take an example of chlorine where we have 35. 35. Yeah, 35. Mass number 35. And then here we put the number of electrons if chlorine is neutral. Then let's take another example. Which other example can we put? Another example. So we can take another example of, can we take oxygen? Let's take an example of oxygen and we put here, let's put here 8. Supposing we put here 8, the number of electrons is 8. The number of electrons is 8. Stop. And here I also put what? 8. Just do like that. So now we are going to complete our table. Supposing we have atomic number, and we said atomic number is the number of protons. So it means here will be 20. Then number of electrons, if the atom is neutral, which we believe this time that is neutral, it will be also here 20 because they are equal for a neutral atom. Then the neutrons will be obviously again 20. Yeah, it's very easy. 20. Why 20? Because neutrons is equal to mass number minus atomic what? Number. Then again now, protons are 6, meaning atomic number will be 6. Then neutrons are 6. So if you want to get the mass number, we get 6 plus what? 6 plus 6. So it will be 12. Then the number of protons is equal to the number of neutrons, which will also be 6. Yeah, 6. Yeah. Then here, let's do this one as our last one. So if we want to get the number of the atomic number will be equal to the number of electrons. If the atom is neutral, so to be 17, even the protons will be 17, and we subtract, that is 35 minus 17, which will be what? 18. So the last number, I leave it as your trial. Make sure you try out the last one. Yeah. So let's continue now, and we talk about isotopes. So isotopes, these are atoms of an element that have the same number of protons and different number of neutrons. Most of the elements exist naturally. Most of the elements that exist naturally exist as what? Isotopes, most of them. So this is why sometime we are going to use these isotopes to calculate what we call the relative atomic mass, meaning the combination of many isotopes. So examples of elements here which have another definition of isotope: same proton number, different mass number. Same number of protons, different number of neutrons. So oxygen, we can have carbon 12, carbon 13, carbon 14. Oxygen 16, oxygen 17, oxygen 18. Hydrogen 1, 2, and 3. Chlorine 35, and chlorine what? 37. So those are examples of our isotopes. So let's try to discuss about the atomic masses. Atomic what? Masses. So atomic masses, we are measured relative to carbon-12 isotope. Normally we do this in every scientific measure is measured relative to something. So it is hard to be independent. So the units are unified atomic mass, or AMU, whereby 1 U or 1 AMU is equal to 1.6 times 10 to the power negative 27 kilograms. So 1 mass of carbon-12 is equal to 12 what? U. Therefore, a 12 of carbon-12, which is 1 U. Okay, that is just a theory. So we may not use it now, but it's good when you know it. So someone is asking here, is asking us to define relative isotopic masses. So we are going to define them. But we define them relative to carbon-12. So we are going to say relative isotopic mass is the mass of an atom of isotope compared with a 12 of the mass of an atom of carbon what? 12. So you see, we are measuring it relative to carbon-12. Carbon-12. So it's a standard of our measure. Then this one is the weighted average mass, because we are going to say that to have the mass of the atom is a combination of many isotopes, as we are going to see in our explanation. So it's the weighted average mass of an atom of an element compared with 1/12. So you'll find that when we have relative atomic masses, this is why we say the units are not very important. We normally divide and the units will cancel out. So chemists combine the contribution of each isotope according to their relative abundance to obtain relative masses of an element. These relative abundance are obtained using the mass spectrometer to see how it helps us to determine or to find our relative atomic masses. But before we continue, let's talk about the meaning of the term relative abundance. So we can say relative abundance is the amount of each isotope present in a given sample of an element. It is actually the contribution of each isotope in determining the relative atomic masses. So we can have two types of relative abundance. Relative what? Is the amount of each isotope present in a given isotope of any element, expressed as a what? A percentage. So you observe each of the isotope will have a given what? Percentage, as we are going to see very soon. Then we have also relative intensity, which is the amount of each isotope present in a given sample of an element, expressed in a measurable property. So here we are saying the amount of each isotope, meaning that if we have, for example, 10 isotopes, and each of those isotopes has a given amount, a given what? Amount. So that amount of each of each of the isotope is what we are going to be calling the relative intensity. It can be expressed in terms of current, in terms of voltage, in terms of ratios, as we are going to see. So we have said that we use the abundance to calculate the relative what? Atomic mass. So it is equal to the summation of abundance divided by 100 times isotopic mass. Then percentage abundance is equal to the intensity of the isotope divided by total intensity times 100. So let's look at some worked example. Example 1a says that a sample of bromine contains 53% of boron and 47% of boron is bromine, not boron. Is 53% of bromine, 79 and 47% of bromine 80. Then they're asking us to determine the relative atomic what? Mass of bromine. The relative atomic mass of what? Bromine. So we are going to say, how do we use our formula? How do we use our formula in the calculations? How do we use our formula in the calculations? So here, example 1a, we are going to say that we say that our relative atomic mass will equal to the summation that is the abundance of abundance divided by 100 times what? Isotopic what? Mass. Isotopic mass, which will equal to, this time we are going to say we have 53 out of what? 100. So make sure you put your calculator very near. Times what? The isotopic mass, which is 79. So today the students are going to help me in the calculations. Me, I'm just going to be illustrating. Then here we shall have 47 out of what? 100. 47 out of 100 times what? 80. So you make sure you calculate this. So this is our illustration. So the contribution of each isotope. So this percentage is for isotope 79, and this percentage is for isotope what? 80. So you're going to calculate, and you make sure you find the what? The answer. You find the what? The answer. Then the last part of the question is telling us to determine the relative atomic mass of so this answer here will be our relative atomic what? Mass. Relative atomic mass. So sometimes they may even ask you to show. They may ask you to show our percentages. To show our percentages and the isotopic mass, in the form of a graph, So this graph is normally, we call it the mass spectrum. Mass what? spectrum, mass spectrum, a mass spectrum. So we have here, we have the spectrum, so mass spectrum. So in this mass spectrum is normally this side here. On this side we put the percentage abundance, which we have got, the percentage abundance, and here we put yeah, we normally we put our isotopic mass. So we can say isotopic what? Mass. So you try out and then you finish. So here we have, if the percentage of one is bigger, these are almost the same. But it's good when the students will find out. Let's just put here 79 and here also 8. Put what? 8. 8. So let's come here also. So supposing we have another question which tells us that a sample, you can say a sample, this time we are going to say a sample of chlorine, Chlorine has the following. So this time we are going to have 75% chlorine what? 35. And then you also have 25% chlorine what? Chlorine 37. So then they tell you to calculate the relative atomic what? Mass. Then this first part, then show. Then part B they tell you show the mass spectrum. Mass what? Spectrum. So we are going to calculate very quickly mass spectrum. So this mass spectrum comes from the mass spectrometer. The mass what? Spectrometer. So here, what we first do, we can first say our relative atomic mass. Relative atomic mass will equal to the summation. So we quote our formula of abundance. If it is percentage abundance, it will be time over 100 times what? Isotopic mass. Then from there, let's go slowly. So we say that 75 out of 100 times what? 35. So we begin with the percentage abundance. That is 75 out of 100 times 35. Then we have also 25 out of 100 times what? 37. So you see, the percentage times the isotopic. So what we have here is our mass. So it can be up, or we say we can put it what? Down. Then from there, we calculate and get our answer. So I told you put your calculators very near and you try to get for me the answer. So answer will be, let me give you like a few seconds to get for me the answer. So our answer will be 35 point what? 5. 35 point what? 5. Thank you very much for that. Then now we want to show the mass spectrum. So we can say our mass what? Spectrum. Mass spectrum. So mass spectrum, as we have said in our illustration, though we didn't finish there, here we can put the percentage abundance. Let's make it like this. The percentage what? Abundance. Percentage abundance. As you said, from the definition of percentage abundance is the amount of each isotope. So meaning the amount of chlorine 35 in a sample of chlorine will be 75%. And the amount of chlorine 37 in a given sample of chlorine we have this time is 25%. So here we can divide and say, because we can say this one can be a better example than that one because the percentages are different. This is why I want to show it to you. So here we can say we have 25, 50, 75, 100. So we say 25, 50, 75, and 100. Then we put our isotopic masses. Isotopic. Isotopic mass. Isotopic what? Mass. Then here we put 1. It's okay even if we don't use a scale here. So from there, our chlorine 35 is 75%. So we do like that. And our chlorine 37 is 25 what? Percent. So here we are going to have, we can even do like this and put 75% to make it look nice. And here we put 25 what? Percent. So we have shown our mass spectrum. So meaning that when you pass this sample of chlorine in the mass spectrometer, you will have a graph like this, which we normally call the mass spectrum. So we shall talk about the mass spectrum in our next lesson. And we do more examples. We do more what? Examples. So let's go back to our slide. I think you've tried to follow what we have done. Let's go back to our slides. Hope you are following and you are enjoying our lesson. So we have another example here, which we have not covered. But if you have the questions here, you can try to calculate. So this example here, what you need to first do is to determine the percentage what? Abundance. Thank you very much for following once again. Hope you've known our definition. God bless you very much and see you next time. Bye-bye.